Module 5, Lecture B, Fitting and Overfitting. By the end of this lecture, you will be able to describe in intuitive terms how training adjusts model parameters to reduce loss, differentiate underfitting, appropriate fitting, and overfitting using examples, and explain why evaluating models only on training data can be misleading. How models adjust from guess to better fit. When we train a model, we begin with an initial guess for its parameters, often random or based on simple rules, so its first predictions are usually poor. We measure how wrong these predictions are using a quantity called loss, where a higher loss means worse performance. Training then consists of repeatedly checking this loss and adjusting the model's parameters to reduce it. Over time, this process refines the model so its predictions become more accurate. Tuning a bread recipe is similar to training a model. Your first loaf might turn out dense and too salty, like a model with high loss. You taste the bread, adjust ingredients such as water and salt, and bake again. In the same way, a model adjusts its internal parameters based on loss feedback to improve its predictions. Each change is meant to reduce loss, just as each recipe tweak aims to improve the bread's texture and flavor. Imagine you are walking downhill in a foggy landscape, where you cannot see far, but can feel which way the ground slopes. The height of the ground represents the loss of a model, with high ground meaning high loss, and the valley floor meaning low loss. Starting from an initial guess, the model takes small steps in the direction that reduces this loss, just as you would keep stepping downhill. By repeatedly adjusting in the direction of lower loss, the model gradually improves its predictions and moves from a rough guess to a better fit with the data. Stepwise model improvement. During training, a model improves by repeatedly checking how wrong its predictions are and adjusting its internal parameters. It starts with initial settings, makes predictions, and compares them to the correct answers to compute a loss, which measures its error. The training process then changes the parameters slightly in the direction that reduces this loss. By repeating this cycle of prediction, loss calculation, and adjustment many times, the model gradually fits the data better. Training a model is like walking down a dark, foggy hill with only a flashlight. The height of the hill represents the loss, and your position represents the model's parameters. You cannot see the whole landscape, but you can sense the local slope and take small steps downhill. In the same way, the training algorithm uses local changes in loss to adjust the parameters step by step, trying to reduce the loss. Sometimes the surface is smooth and progress is easy, while other times it is bumpy and requires more steps or different step sizes to keep moving downward. Learning often improves through small, repeated adjustments, much like a musician practicing a new piano piece. At first, their timing and dynamics are off, similar to a model starting with high loss. By listening, spotting mistakes, and focusing on those areas in each practice session, they gradually refine their performance. Each session is like a training step, where performance is evaluated and targeted changes are made. Over time, these incremental refinements lead to a polished result, just as consistent parameter updates help a model better capture patterns in data. Seeing parameters move. You can think of a model's parameters as adjustable knobs that control how it behaves. At first, these knobs are set randomly, so the model makes poor predictions and the loss is high. During training, the learning algorithm measures the model's errors and slightly adjusts the knobs to reduce those errors. With each batch of data, the parameters shift a bit more, gradually moving the model from rough initial guesses toward a more accurate configuration. Modern models have too many parameters to track individually, but we can understand them through a simple example. Imagine a model predicting house prices using only size and age, where one parameter controls how strongly size affects price and another controls the effect of age. If the model undervalues size, it predicts prices that are too low for large houses. So the learning algorithm increases the size parameter. If it overemphasizes age, it predicts prices that are too low for older houses, so the algorithm reduces the age parameter. By repeatedly adjusting these parameters based on such errors, the model gradually captures the true relationships in the data and reduces its loss. Training a model is like learning to shoot basketball free throws. At first, the player often misses, just as a model makes prediction errors. After each shot, the player adjusts strength and angle based on feedback, similar to how a model updates its parameters. Over time, these repeated adjustments lead to more accurate and consistent shots, just as the model gradually reduces its loss. In both cases, the final pattern of adjustments produces reliable performance without needing constant real-time changes. Python code, seeing parameters move. This script demonstrates how model parameters change during a simple training process. It uses a tiny linear model and updates the weights manually. As training progresses, the loss value decreases while the weights gradually adjust. The main idea is to show how repeated updates can steadily improve the model's performance. We begin by importing two key Python libraries, numpy and the pyplot module from matplotlib. Numpy handles numerical operations efficiently, especially with arrays and mathematical functions. Pyplot is used to create visualizations, such as graphs and charts. Together, they allow us to perform numerical computations and then visually represent the data and results, which is essential for the tasks in this script. We begin by setting the random seed in the numerical library to 0, so that any random numbers generated are the same every time the program runs. This makes the code deterministic and ensures that results can be reproduced consistently. Reproducibility is important because it allows us to debug more easily and verify that the code behaves as expected across different runs. We start by creating a small synthetic dataset that follows a simple straight line. The true line has a weight of 2 and a bias of 1. To build this dataset, we generate 20 evenly spaced input values between 0 and 5 using a numerical tool. This setup gives us a clean linear relationship that we can later use to simulate a linear model with added noise. We begin by generating random noise from a normal distribution with a mean of 0 and a standard deviation of about 1/2. And we add this noise to our data to make it more realistic. Then we compute the target values by taking each input value, multiplying it by the true weight, adding the true bias, and finally adding the noise. This process creates data that follows an underlying linear relationship, but includes random variation, similar to what we see in real-world measurements. We begin by choosing initial values for the model's weight and bias, on purpose making them poor guesses. The weight is set to -1 and the bias is set to 5. These suboptimal starting values are intentional because they let us see how the training process gradually adjusts the parameters. As training progresses, the model updates the weight and bias to values that better fit the data. We set the learning rate to 0.05 to control how much the model parameters change at each training step. A smaller learning rate makes smaller updates, which can lead to a more precise solution, but usually requires more time. We also choose 20 training steps, meaning we update the parameters 20 times to reduce the loss. With this setup, the model's predictions are gradually improved by repeatedly adjusting the parameters in small steps. We begin by creating 3 empty lists to track how training progresses. One list will store the changing weight values, another will store the bias values, and a third will record the loss at each step. By keeping this history, we can later examine how the model's parameters evolve during training and how the loss decreases as the model learns. This function computes predicted outputs using a simple linear model. It takes input values, a weight, and a bias, then multiplies the inputs by the weight and adds the bias to produce predicted values. This represents a basic linear relationship, which is central to linear regression. The predictions can then be compared with actual data to evaluate how well the model is performing and to adjust the weight and bias during training. This function computes the mean squared error loss, a common measure of how far predictions are from the true values. It first finds the difference between each true value and its corresponding prediction, then squares these differences to make them positive and to highlight larger errors. After that, it takes the average of all the squared differences to produce a single number that represents the typical error size across all predictions. Finally, this result is converted to a floating point number for consistent numerical use. During training, we repeat a loop for a fixed number of steps. In each step, we use the current weight and bias to generate predictions with our linear model. We then compare these predictions to the true target values using the mean squared error loss. This loss tells us how far our predictions are from the actual values and guides how we should adjust the model parameters. To update a simple model, we first find the error by subtracting the true values from the predicted values, which shows how far off the predictions are. We then compute the gradient for the weight by taking the average of 2 times this error, multiplied by the input values, which tells us how the weight should change to reduce the error. In the same way, we compute the gradient for the bias by taking the average of 2 times the error, which shows how the bias should be adjusted. These gradients are then used to update the model's parameters in the direction that minimizes the loss. In gradient descent, we update the model parameters by moving them in the opposite direction of the gradient of the loss. This means we adjust each weight by subtracting the learning rate multiplied by the gradient of that weight. We do the same for each bias, subtracting the learning rate times its gradient. Repeating this process step by step gradually reduces the loss and refines the model parameters. We keep track of how the model changes during training by storing the weight, bias, and loss values at each step. Recording the weight and bias over time lets us see how the parameters evolve. Tracking the loss shows how the error decreases as training progresses. This history is important for later analysis and for visualizing the training process. We first report the initial guesses for the weight and bias, -1 and 5, to establish a baseline. Then we show the final learned weight and bias, rounded for clarity, to see how close the model came to the true values. We also state the true underlying weight and bias, which are 2 and 1, as a reference for how well the model has learned. Finally, we compare the first recorded loss value with the last recorded loss value, both rounded, to highlight how much the model's prediction error decreased during training. We set up a visualization to track how both the model parameters and the loss change during training. Using a plotting library, we create a figure with 2 side-by-side panels in a single row. The figure is sized to clearly display the information. This layout lets us directly compare how the loss and parameter values evolve over time as training progresses. We visualize training progress by plotting the loss value at each training step. The horizontal axis shows the step index, and the vertical axis shows the mean squared error loss. Each point is marked and connected to form a line. and the plot is given a title that highlights how the loss shrinks as the parameters are updated. This simple visualization helps us see how the model's error decreases over time as it learns. In the second subplot, we show how the weight and bias change over the training steps. We plot the stored history of the weight as one line and the history of the bias as another. To give a reference, we add horizontal lines for the true weight and true bias values, using different line styles so they are easy to distinguish. The title explains that the parameters are being nudged toward better values, and the axes indicate training step index and parameter value magnitude. A legend identifies each line so listeners can understand which curve represents each parameter and its true value. The layout adjustment command makes sure all subplots fit neatly inside the figure, so labels and titles do not overlap or get cut off. After that, the display command shows the final figure on the screen. This lets us visually examine how the loss and parameter values change over the training steps. This script shows how a simple linear regression model learns by manually updating its weight and bias to reduce prediction error. It starts with poor initial guesses, then uses gradient descent with a small learning rate to adjust the parameters or 20 training steps. As training progresses, the mean squared error steadily decreases, meaning the model's predictions get closer to the synthetic data. By the end, the weight and bias move toward the true values used to generate the data, and plots of the loss and parameter values over time illustrate how the model converges during training. Model complexity balance. Underfitting simple models. Underfitting occurs when a model is too simple to capture the important patterns in the data, even if it is trained thoroughly. In this situation, the model misses key relationships and makes large errors on both the training data and new data. For example, predicting housing prices using only the city's average price while ignoring factors like neighborhood and size will consistently produce inaccurate results. The problem is not a lack of training, but that the model does not have enough flexibility to represent real-world relationships. Underfitting happens when a model is too simple to capture the real pattern in the data. For example, fitting a straight line to data that actually follows a curve will always leave systematic errors because the line cannot bend. In practical fields like medicine or education, using overly simple models, such as predicting patient risk using only age, can lead to consistent misclassifications. These models ignore important variables and therefore produce significant and predictable inaccuracies. Recognizing underfitting is important because overly simple models can produce biased predictions and large errors even on the training data. Unlike overfitting, where a model performs well on training data but poorly on new data, underfitting leads to poor performance everywhere because the model fails to capture the true structure of the data. This can appear in systems like recommendation engines that ignore individual preferences or financial models that cannot distinguish different risk levels. Detecting these problems shows when a model is too simple and needs more features or a more flexible design to better reflect real-world complexity. Overly complex models. Overfitting happens when a model is too complex and starts capturing noise instead of the true patterns in the data. For example, a simple line through data points may miss some points but still show the overall trend, while a very complex curve can pass through every point, including outliers. This complex curve looks very accurate on the training data but fails on new data because it is essentially memorizing instead of learning. As a result, the model appears to have perfect training performance but cannot generalize to new situations. When predicting house prices from features like size, number of bedrooms, and neighborhood, a moderately complex model can learn general patterns, such as larger homes in desirable areas costing more, and make reasonable predictions for new houses. An overly complex model, however, may start memorizing specific quirks in the training data, like an unusually high price caused by a bidding war. Such a model can fit the training data almost perfectly, but perform poorly on new data because it has not captured the stable relationships between features and prices. Instead, it relies on details that do not reliably appear in future cases. Overly complex models can cause problems in many areas, not just in numerical prediction. In medical diagnosis, a flexible model trained on limited data from one hospital might latch onto irrelevant details, such as machine artifacts, instead of true clinical signs, so it works there, but fails in other settings. In credit scoring, a similarly complex model might overfit to short-term economic conditions and then perform poorly when those conditions change. In all these cases, the model is learning noise and coincidences rather than stable patterns, which boosts training performance but harms real-world reliability. Python code. Overly complex models. This script illustrates the idea of overly complex models in an intuitive way. It compares simple and complex curves fitted to noisy data and examines how they behave. The main goal is to show how increasing model complexity influences generalization performance, or how well the model works on new, unseen data. We start by importing the numerical library numpy, which lets us work efficiently with arrays and perform mathematical operations. We also import the pyplot module from the matplotlib plotting library. This plotting module is used to create visualizations, such as plots and graphs, so we can see and interpret our data and model results more easily. We set a fixed random seed using the numerical library's random seed function with the value 42 to make our results reproducible. This means that every time the script runs, it generates the same sequence of random numbers. Having consistent random values allows us to reliably repeat experiments, debug issues, and verify that our models behave as expected. To create input data for our training examples, we use a numerical tool that generates 10 evenly spaced values between 0 and 1. These values form a simple one-dimensional set of input features for the training data. Using 10 points provides enough data to fit a model while keeping the example small and easy to understand. We assume a simple linear rule that defines the true relationship between each input and its output. For every training example, we take the input, multiply it by 2, and then add 1 to get the true output. This rule serves as the underlying pattern in the data. We will later compare this ideal linear relationship to noisy observations and to the models we train. We add random noise to our training targets to make them more realistic and better reflect imperfect real-world data. This noise comes from a normal distribution centered at 0 with a standard deviation of 0.1. Its shape matches the training inputs, so that each example receives its own noise value. This process helps us evaluate how well our models can handle variability in the data. In this step, we create noisy training targets by adding random noise to the true underlying relationship. This mimics real-world data, where measurements are rarely perfect and often contain errors from various sources. By combining the true values with noise, we generate a more realistic dataset for the model to learn from. This allows us to see how well the model can generalize when trained on imperfect, noisy inputs. We create a dense set of test inputs by generating 100 evenly spaced values between 0 and 1. This grid of points serves as unseen data that was not used during training. By evaluating our models on this range of inputs, we can see how well they generalize beyond the training set. This approach gives us a clearer picture of their performance on new data. We now compute the true outputs for the test inputs without adding noise. To do this, we apply the same linear rule used for the training data, where each test input is multiplied by 2 and then increased by 1. These noise-free values form a clean reference line. We then compare our model predictions to this line to see how well the models generalize to new data. We fit a simple linear model to the training data using a function that finds the best straight line through the points. By setting the degree to 1, we are specifically looking for a line rather than a more complex curve. The function returns the slope and intercept that minimize the difference between the predicted values and the actual training values. This lets us see how well a basic linear model captures the main trend in the data. We fit a very complex model to the training data by using a numerical tool that finds the best fitting polynomial. In this case, the polynomial has degree 9, meaning it is a 9th degree curve. Such a high degree model can closely match intricate patterns in the training data. However, it also increases the risk of overfitting, where the model fits the training data too specifically and may perform poorly on new, unseen data. We use the simple model's coefficients to predict the outputs for the training data by feeding these coefficients and the training inputs into a polynomial evaluation function. This function applies the simple linear model to each input value and produces a set of predicted outputs. By comparing these predictions to the actual training outputs, we can judge how well the simple model fits the training data. This evaluation will later be used to compare the simple model's performance with that of the more complex model. We use the coefficients of the complex polynomial model to predict the outputs for the training data by evaluating the polynomial at each training input. A numerical tool, such as a polynomial evaluation function, takes these coefficients and input values to compute the predicted outputs. This step lets us see how closely the model matches the training data and helps us judge whether the model might be overfitting, meaning it fits the training data very well but may perform poorly on new, unseen data. We now evaluate the simple model on a dense set of test inputs to see how it behaves on unseen data. Using a polynomial evaluation function from a numerical library, we provide the model's coefficients and the test input values. The function applies the polynomial defined by these coefficients to each test point and returns the predicted outputs. This process is essential for judging how well the simple model generalizes beyond the data it was trained on. We use the numpy library to evaluate our complex polynomial model on a dense set of test inputs. Using the coefficients learned from the training data, we apply the model to these new input values to generate predicted outputs. We can then compare these predictions to the true outputs to measure how well the model performs. This process is essential for judging how well the complex model generalizes to new, unseen data. We use a helper function to compute the mean squared error, a common way to measure how well a model performs. The function first checks that the true values and the predicted values have the same shape, because a mismatch would cause calculation errors and unreliable results. After confirming they match, it calculates the average of the squared differences between the true and predicted values. This single number represents the typical size of the prediction error and shows how closely the model's outputs align with the actual data. This line computes the mean squared error between the true values and the predicted values. It finds the difference for each pair, squares these differences so they are all positive, and then takes their average. The final result is converted to a floating point number to keep it consistent for later numerical calculations. We now compute the training error for the simple linear model using the mean squared error measure. This measure compares the actual training targets with the model's predicted values and calculates the average of the squared differences between them. The resulting value tells us how well the simple model fits the training data and is stored as the mean squared error for the model on the training set. We now compute the training error for the complex polynomial model using the mean squared error. This measure compares the actual training targets with the model's predictions on the training data and averages the squared differences between them. The resulting value tells us how well the complex model fits the training data. Later, we can compare this training error to the test error to assess how much the model may be overfitting. We evaluate the simple linear model on test data by computing its test error using the mean squared error. This measure compares the true test outputs with the model's predicted outputs. It does so by taking the squared differences between each pair of true and predicted values and then averaging them. The resulting value tells us how well the simple model generalizes to new unseen data. To evaluate the complex polynomial model, we compute its test error using the mean squared error. This measure compares the model's predicted outputs on the test data with the true test outputs. A lower mean squared error means the model's predictions are closer to the actual values. In this way, the mean squared error tells us how well the complex model performs on unseen data. We report a brief summary of mean squared errors for both models to compare their performance. We first present the training error for the simple model, rounded to 4 decimal places, followed by the training error for the complex model with the same precision. We then give the test error for the simple model, again rounded to 4 decimal places, and finally the test error for the complex model. This compact set of values lets us quickly see how each model performs on both training and test data. We begin by creating a plot with a clear, moderate size, so we can visualize our data and the behavior of different models. This figure lets us place the true relationship and the predictions from both the simple and complex models on the same axes. By looking at them together, we can directly compare how well each model fits the data and how effectively it generalizes beyond the observed points. We use a scatter plot from the plotting library to show the training data as black points. This lets us clearly see the noisy data that the models are trying to fit. We also label these points as training data so they can be easily identified in the plot legend. This line uses a plotting library to show the true relationship between the input and output data. It draws a simple line based on the test inputs and their correct outputs. The line is colored green so it stands out from other plot elements. It is also labeled as the true relationship so it can be clearly identified in the legend. We use matplotlib to plot how the simple model predicts on the test data. The horizontal axis shows the input values from the test set, and the vertical axis shows the model's predicted targets. The prediction line is drawn in blue and labeled as the simple model, so it is easy to identify. This plot helps us judge how well the simple model generalizes to data it has not seen before. We use matplotlib to plot the complex model's predictions on the test data, with input values on the horizontal axis and predicted targets on the vertical axis. The model's prediction curve is shown in red and displays many sharp fluctuations. These wiggles indicate that the model is overfitting because it is capturing random noise in the data instead of the true underlying pattern. This visualization makes the overfitting behavior clear and easy to interpret. Label the horizontal axis as input feature value and the vertical axis as target value, so it is clear what each axis represents. Then include a legend on the plot to identify the different lines and markers. This makes it easier to compare the true relationship with both the simple model and the complex model, and to understand how they differ. We use a plotting library to display the final graph, which shows the true relationship along with both the simple and complex models. Seeing them together lets us directly compare how each model follows the underlying pattern. By examining this visualization, we can judge how well each model fits the data and how effectively it might generalize to new inputs. This script compares a simple linear model with a more complex ninth-degree polynomial model to show how model complexity affects generalization. It creates noisy data from a true linear relationship and fits both models to this data. The linear model captures the underlying trend well on both training and test sets, indicating good generalization. The complex polynomial model fits the training data almost perfectly, but overfits, leading to poor performance on the test data. This is confirmed by the mean squared error values, where the complex model has lower training error but higher test error, and by the plotted curves, where the simple model is smooth and close to the true relationship, while the complex model fluctuates excessively. Balanced model fit. A balanced model fit finds the middle ground between underfitting and overfitting by capturing the main structure of the data without chasing every small fluctuation. You can think of it as a smooth curve that follows the overall trend of the data points, rather than matching each one exactly. It is complex enough to learn real relationships, such as why larger homes in better locations cost more. But it does not contort itself to explain rare or unusual cases. The goal is a model that performs well on the training data and still maintains its accuracy on new, unseen data, leading to reliable predictions in real-world situations. In medical diagnosis using patient records, an underfit model might rely on just one symptom, such as fever, and miss many real cases, while an overfit model might memorize irrelevant details like the exact visit time and treat them as important. A well-balanced model instead focuses on meaningful combinations of symptoms and risk factors, and ignores details that are unlikely to repeat. This balance helps the model make predictions that remain accurate and useful across different hospitals and patient populations, which is essential for real-world healthcare use. To achieve a balanced model fit, you must choose an appropriate level of complexity and apply constraints so the model avoids extreme behavior. In business forecasting, this means capturing real seasonal and long-term trends without chasing random events like sudden sales spikes. In education, it means relying on stable predictors such as grades and attendance instead of overreacting to unusual test scores. Overall, the model should align with expert knowledge and common sense, capturing meaningful patterns rather than coincidences, so that decisions remain reliable in complex environments. Generalization beyond training. Training versus unseen data. When we train a model, we adjust its parameters using training data so its predictions match known outcomes. But our real goal is for it to work well on new, unseen cases. For instance, a medical diagnosis model should not only classify past patient records correctly, but also handle future patients with new combinations of symptoms. This means we must evaluate models on data beyond the training set, because judging them only on the examples they were trained on can give a misleading picture of their real-world usefulness. Learning can be compared to a student who memorizes answers to practice questions. If the test repeats those questions, the student may do very well. But if the test asks new questions that use the same ideas in different ways, their performance may drop if they never understood the concepts. In the same way, a model trained only on specific examples can look strong on that training data, but fail when faced with new, varied inputs. This shows that real-world success requires capturing the deeper patterns, not just memorizing particular cases. Generalization is a model's ability to use what it has learned to handle new, similar cases that were not in its training data. A model that generalizes well captures the essential patterns in the data rather than relying on quirks or noise that only appear in the training set. For example, a digit recognition model should recognize many handwriting styles, not just the ones it has seen before. If we judge a model only by its performance on the training data, we may wrongly believe it is reliable, even though it could fail on the more varied data it will face in real-world use. Limits of memorization. When a model memorizes its training data, it stores exact input and output pairs instead of learning the underlying patterns. This is similar to memorizing exam answers without understanding the concepts, which fails when questions are asked in a new way. A model that behaves this way is overfitting. It has very low error on the training data, but performs poorly on new, slightly different data. If we only evaluate on the training set, the model can appear successful, even though it has not truly learned to generalize. A spam detection model trained only on old emails may simply memorize specific phrases and patterns, so it appears accurate on that training data, but fails when spammers change their tactics. In contrast, a model that captures broader patterns such as tone or intent is more likely to recognize new forms of spam. Evaluating performance only on the training set cannot tell us whether the model has learned these deeper patterns or just memorized outdated details. This is why it is crucial to test models on varied, unseen data to ensure they truly generalize. A medical diagnosis model trained on records from only one hospital may simply memorize specific patient details and appear accurate on that limited data. However, patients and practices at other hospitals can differ, and even small changes in data entry or treatment can cause such a model to fail. As a result, its performance can drop sharply when used in new settings. Evaluating the model only on its original training data hides these risks and rewards memorization instead of true ability to handle diverse, real-world cases. Why separate evaluation? If we only test a student on practice questions they have already seen, they may look skilled but still fail on new problems. Machine learning models can behave the same way, performing well on training data but struggling with new situations. To check whether a model has truly learned patterns that generalize, we must evaluate it on a separate set of data it has never seen before. This separate evaluation set reveals how well the model is likely to perform in real, unseen scenarios. When a model is very flexible or complex, judging it only by how well it does on the training data can be misleading, because it may simply memorize that data, including random noise. For instance, a house price model might latch onto unimportant details that just happen to correlate with price in the training set, such as an overrepresented neighborhood. This can make the model look accurate on the data it has seen, but those false correlations usually fail on new cases, causing performance to drop. Using a separate evaluation set helps expose this gap between apparent success on the training data and true reliability on unseen data. Using separate evaluation data is essential for making sound choices when developing a model. When you change the model's design or tune its hyperparameters, you need to see whether it truly improves generalization, rather than just fitting the training data more closely. If you rely only on training performance, you risk building an overly complex model that looks good on past data, but fails on new, real-world cases. Evaluating with separate data helps ensure the model is not just memorizing, but can act as a reliable decision maker for future situations. Python code. Why separate evaluation? This script explains why it is important to evaluate a model on data separate from the training set. It compares training error and test error in a setting where the model may simply memorize the training examples. By looking at both errors, we can see whether the model truly generalizes beyond the data it has already seen. The main goal is to highlight that low training error alone does not guarantee good performance on new, unseen examples. This script assumes that the numpy and matplotlib libraries are already available, as they usually are in a Colab environment, so you normally do not need to install them yourself. If you run the script in a different setup where these libraries are missing, there is a commented instruction showing how to install numpy, matplotlib, and seaborn using a package manager. This serves as a backup option to help the script run smoothly across various environments. We start by importing a numerical computing library to efficiently work with arrays and perform mathematical calculations. We also import a plotting library that lets us create visualizations. Together, these tools allow us to process data, build models, and then plot both the data and the model predictions to visually compare how well the model performs. We set the random seed to 0 using the random tools in the numpy library, so that any random numbers generated will be the same every time we run the script. This makes our results reproducible, meaning we can reliably repeat experiments and get identical outcomes. Reproducibility is especially important when debugging code or comparing different runs of a program. We begin by generating a simple set of input features using a numerical tool that creates evenly spaced values. Specifically, we create 20 values between 0 and 1. These values form a one-dimensional input feature set for our model. This gives us a small, controlled dataset that is easy to work with and understand. We are modeling a simple linear relationship and adding a bit of randomness to make it more realistic. Each input value is multiplied by 2 and then increased by 1 to create a basic linear trend. To simulate measurement imperfections, we then add small noise drawn from a normal distribution with a mean of 0 and a standard deviation of about 0.05. The result is a set of target values that mostly follow a straight line but include slight variations, similar to real-world data. We divide our dataset into a training set and a test set. The first part of the data is used for training the model, and the remaining data is kept separate as the test set. This setup lets us fit the model on one portion of the data and then evaluate how well it performs on data it has not seen before. Doing this is essential for checking how well the model is likely to generalize to new, unseen examples. We divide the target values into a training set and a test set. The first part of the true target values is used for training the model, and the remaining values are reserved for testing. This separation lets us check how well the trained model performs on data it has not seen before. In this way, we can better judge how well the model is likely to generalize to new, unseen data. Before doing more calculations, the code first checks that the training input and target arrays have matching shapes. This means every input feature must line up with a corresponding target value. Ensuring this match is essential because it allows the model to learn correctly from the data and be evaluated accurately. We use a helper function to compute the mean squared error, a standard measure of how accurate our predictions are. Before doing the calculation, the function checks that the true values and predicted values have the same shape. This is enforced with an assertion that stops the program if the shapes do not match. By doing this, we ensure the data is properly aligned and the error calculation is valid. This line computes the mean squared error between the true values and the predicted values. It first checks that both arrays have the same shape. Then it finds the difference between each true and predicted value, squares these differences, and takes their average. Finally, it converts this average to a floating point number for precision and returns it as the result. To train a simple linear model using a closed-form solution, we first build a design matrix by combining a column of 1s with the training input values. The column of 1s represents the intercept term, so the model can learn a bias in addition to the slope. We then transpose this combined array so its dimensions match what we need for matrix calculations. With this design matrix in place, we can efficiently apply the normal equation to solve for the model parameters. To find the parameters of our linear model, we use the normal equation, which relies on the pseudo-inverse of the design matrix. Using a linear algebra tool, we compute this pseudo-inverse, then multiply it by the transpose of the design matrix and by the training target values. The result is a parameter vector that contains both the intercept and the slope of the line. This method gives us the best fit line that minimizes the error on the training data. We take the intercept and slope from the parameter vector that was previously computed using the normal equation. The first value in this vector is the intercept, and the second value is the slope. We then convert both values to standard floating point numbers so they are ready for later calculations and predictions. To make predictions on the training set with a linear model, we start with the intercept and add the slope multiplied by each training input. This calculation gives a predicted output for every data point. These predicted values represent what the model expects based on the assumed linear relationship. We then use them to judge how well the model fits the training data. To make predictions on the test set with a linear model, we use the learned intercept and slope from training. For each test input, we multiply the input value by the slope and then add the intercept. This applies the same linear relationship found in the training data to new, unseen data. By doing this, we can check how well the model generalizes beyond the training set. To measure how well a linear model fits the training data, we use the mean squared error. This error measure compares the actual target values in the training set with the values predicted by the model. It calculates the average of the squared differences between these actual and predicted values. A smaller mean squared error indicates that the model's predictions are closer to the true training targets. To evaluate our linear model, we compute the test mean squared error. This uses a function that compares the true target values in the test set with the model's predicted values. It calculates the average of the squared differences between them. The resulting value tells us how well the model is likely to perform on new, unseen data. We make a separate copy of the training target values and store it in a new variable used for memorization. This is important because the memorization model will rely on these stored targets to make its predictions. By copying the targets instead of using the original data directly, we protect the memorization model from any later changes to the training data. This helps maintain the integrity of the stored values and supports accurate predictions. This function predicts values using a nearest neighbor method based on training data. Before making predictions, it checks that the training inputs and their target values have matching shapes. This verification is essential because the later steps rely on the data lining up correctly. By enforcing this match, the function helps avoid errors caused by inconsistent data dimensions. The code sets up an array to hold prediction results for new data inputs. It uses a numerical library to create this array filled with zeros and matches its shape to the shape of the new inputs. This means each input has a reserved spot where its predicted value will be stored. The array is then ready to be filled during the prediction step. For each new input value, we compare it to all training inputs by computing the absolute difference to each one, which gives us the distance to every training point. We then find the smallest of these distances to locate the nearest neighbor in the training set. Using the index of this nearest neighbor, we assign its target value as the prediction for the current input. Repeating this process for all new inputs produces the full set of predictions. The function returns an array of prediction values, one for each new input. For every new input, it finds the closest matching input from the training data, and then uses that training example's target value as the prediction. In other words, each prediction is simply the target value of the nearest neighbor in the training set. To evaluate the memorization model, we generate predictions for the training data using the nearest neighbor rule. We call the prediction function with the training inputs and their targets, and we also use these same inputs as the points to be predicted. This process measures how well the model can reproduce the training data by finding for each input the closest matching example within the training set itself. We now use the memorization model to make predictions on the test data. A function called memorizePredict takes the training inputs, their stored target values, and the new test inputs. For each test input, it finds the closest training example and uses that example's target as the prediction. This shows how a memorization approach can match the training data perfectly, but often fails to generalize well to new, unseen data. To evaluate the memorization model, we compute its training error using the mean squared error. This measure compares the true training values with the model's predictions and calculates the average of the squared differences between them. A smaller mean squared error means the model's predictions are closer to the actual training values. In this way, the training error tells us how accurately the model has memorized the training data. To evaluate the memorization model, we compute its test mean squared error. This uses a mean squared error function that compares the true target values in the test set with the model's predictions. It calculates the average of the squared differences between these true and predicted values. The resulting value tells us how well the memorization model generalizes to new, unseen test data. We report the mean squared error of the linear model on the training data, rounded to 4 decimal places for clarity. This single value summarizes how closely the model's predictions match the training examples. By comparing this training error with the error on the test data, we can assess how well the model is performing and how well it may generalize to new data. We report the test mean square error for the linear model to see how well it generalizes to new, unseen data. This test error can then be compared with the training error to check for overfitting or underfitting. It also allows us to compare the linear model's performance with that of the memorization model on the same task. The code reports the mean squared error of the memorization model on the training data, rounded to 4 decimal places. This error is extremely small, showing that the model fits the training points almost perfectly. However, this near-perfect fit only reflects how well it memorizes the training data, and does not guarantee good performance on new, unseen data. We report the memorization model's test mean squared error to show how poorly it generalizes beyond the training data. The error value is rounded to 4 decimal places for clarity, and then presented with a short descriptive message. This comparison between the model's performance on training and unseen test data highlights its limitations when applied to new examples. We generate a dense grid of 100 evenly spaced values between 0 and 1. This grid serves as the input range over which we evaluate our models. By computing and plotting the model predictions at these points, we can see how the models behave across a smooth, continuous span of input values. We now use the linear model to make predictions over a dense range of input values. Using the previously computed intercept and slope, we calculate a predicted output for each point in this range. In other words, we apply the linear equation across many input values to see how the model's predicted line extends over the entire input space. This helps us visualize the model's overall behavior. We use the memorization model to make predictions on a dense grid of input values by applying a function that predicts each output from its nearest training neighbor. To do this, we provide the original training inputs and their targets, along with the new grid of input points. The function then returns a predicted value for every point on the grid. This lets us see how the memorization model behaves across a continuous range of inputs. We start by creating a new figure using a plotting library, which gives us a blank canvas of a chosen size. This prepares the space where we will display both the data and the model's predictions. Setting up the figure first helps organize the visual output and ensures it fits properly within the viewing area. This line uses a plotting library to create a scatter plot of the training data. The horizontal axis shows the training inputs, and the vertical axis shows their corresponding target outputs. Each data point is drawn as a blue circle. A label is also added, so these points are clearly identified as the training data in the plot legend. We use matplotlib to create a scatter plot that highlights the test data points. These test points are shown as orange triangles, so they are visually distinct from the training data, which is plotted in a different style. We also add the label test points to the legend, so listeners can clearly understand which markers represent the test data when interpreting the graph. We visualize the linear model by plotting its predictions over a dense range of input values. Using a plotting function, we draw a green line that shows the predicted outputs of the model across this range. The line is labeled as the linear model, so it can be identified in the legend. This plot helps us judge how well the linear model fits the data over the entire input space. The code uses the step plotting function from the visualization library to show the memorization model's predictions as a step-like curve. This curve represents how the model chooses outputs based on the nearest training data point. The steps are centered between data points to reflect this behavior. The line is colored red and given a label so it can be clearly identified as the memorization model in the legend. This code uses a plotting library to set the label for the x-axis of a graph. The label explains that the horizontal axis shows the input feature values. Providing this label helps viewers quickly understand what the x-axis represents in the context of the data being visualized. The code sets the label of the y-axis on the plot to target y value. This label explains that the vertical axis represents the target variable in the dataset. By clearly naming the axis, the plot becomes easier to interpret. Viewers can quickly understand what the plotted values mean, making the visualization more informative. The code adds a legend to the plot to explain what each visual element represents. It uses the legend function from the plotting library, which automatically creates entries based on the labels already defined in the plot. The legend's position is set to the best location, meaning the library chooses a spot that avoids covering important data. This helps keep the legend clear and easy to read. We add a title to the plot using the title function in matplotlib to clearly state the main idea of the visualization. The title emphasizes that the plot compares how well the models fit the training data with how well they generalize to separate test data. This makes it easier for viewers to immediately grasp the focus of the plot, which is essential for correctly interpreting the model evaluation results. The final step of the script uses a plotting library to display the completed graph. This graph shows the training data, the test data, and the predictions from both the linear model and the memorization model. By looking at this visualization, you can directly compare how each model behaves on new data. It highlights how well each model generalizes beyond the training examples and makes their performance differences clear. This script compares a linear model with a memorization model to show why separate evaluation is crucial in machine learning. It creates a noisy linear dataset, splits it into training and test sets, and trains the linear model using a closed-form solution. The memorization model predicts each new point using the nearest training example, so it matches the training data perfectly. However, when evaluated on the test set, the linear model has lower error and generalizes better, while the memorization model performs poorly on unseen data. A plot with a smooth line for the linear model and a step-like curve for the memorization model illustrates how memorization leads to overfitting, and why models must be judged by how well they generalize beyond the training set. In this lecture, you learned to describe in intuitive terms how training adjusts model parameters to reduce loss. Differentiate underfitting, appropriate fitting, and overfitting using examples. and explain why evaluating models only on training data can be misleading. In the next module, Module 6, we will go over evaluation metrics. Thank you for your attention. See you all in the next lecture.